Welcome back to the deep dive. Today, we are walking right onto the shop floor. We're tackling one of those persistent industrial headaches. You know the one.
I do. The one that causes sleepless nights for engineers and just eats profit margins for breakfast.
Exactly. Tool wear, coarse surface finish, and those cripplingly slow cycle times, all because chips just won't get out of the way.
That is the sound of money just draining away. I mean, you know the scenario. You're running a tough job, maybe a deep pocket in aerospace-grade titanium.
Or a long run of medical parts in stainless steel.
Right, and your standard flood coolant system is, well, it's just failing. No matter how much volume you pump, the spinning spindle just slings it everywhere but the cutting zone.
It's a classic case where the tool itself becomes a victim of its own success. That old-school coolant dripping down the side is a reactive measure, isn't it? It's trying to wash away debris after the fact.
It is.
So our mission today is to deep dive into the alternative. Through Spindle Coolant, or TSC, we really need to know if that massive investment is worth the transformation in performance.
Well, our sources suggest the distinction is pretty fundamental. Standard coolant is, perfectly adequate for general purpose stuff.
Like aluminum, brass, shallow cuts.
Exactly. It's cheap, it's simple, it's forgiving. But if your work requires deep hole drilling, aggressive material removal in tough alloys,
Or you run high volume production where shaving seconds off the cycle time is everything.
then TSC moves from being a luxury to really an essential requirement.
So we're not just talking about improving a process, we're talking about fundamentally changing the physics of how that machine operates. Let's start with the most obvious pain point TSC solves, the inefficiency of deep drilling.
Ah, yes. We have to talk about the dreaded PEC cycle. If you've ever spent time near a VMC trying to drill a deep hole with standard flood coolant, you hear that agonizing rhythm.
That in, stop, out spray. In, stop, out spray. It sounds painful.
It's the machine babysitting itself. It's slow, repetitive.
So why does it even have to do that?
Because the standard flood coolant just can't get down into the hole to reach the cutting zone. The chips, especially in gummy materials like stainless, they just pack up in the flutes.
And that increases friction, load, heat, all the bad stuff.
Dramatically, the machine knows if it keeps pushing, the tool will just break, or the part will overheat and distort. So the PEC cycle is a necessary evil, a reactive defensive strategy to clear the debris.
It's basically accepting a massive loss of productivity just to save the tool. Okay, so let's pivot. Let's talk about the proactive power of TSC. How does it physically overcome that obstacle?
Well, TSC uses the coolant as a high-pressure energy source. Instead of being poured on externally, the fluid is routed through channels inside the spindle through the tool holder.
And then fired directly out of the tooltip.
Exactly, right where the chip is being formed. And we're talking about pressures from, say, 300 psi all the way up to 1,000 psi.
1,000 psi. That's the kind of pressure you use to cut steel in some applications.
Mm-hmm.
So the fluid isn't just lubricating, it's literally doing mechanical work.
Precisely. It's a hydraulic ram. That focused stream, delivered at high velocity, it hits the newly formed chip, forcibly breaks it, and then blasts up and out of the hole. Instantly.
So it completely bypasses the need for pecking.
In most deep hole applications, yes. Especially anything over a 5-to-1 depth-to-diameter ratio.
That's where the true breakthrough is, the continuous, uninterrupted feed. I mean, if you eliminate 20 pecks in a deep hole, you instantly gain a massive amount of time. What did the source material show for actual productivity metrics?
The numbers are compelling enough to justify the whole cost. In one example they cited, drilling multiple deep features using the standard methods took over 40 seconds.
Because of all the pecking and retracting.
All of it. By switching to TSC, which allowed for continuous drilling, that same operation was reliably done in just 20 seconds.
Half the time. A 50% cycle time reduction. That's staggering. It immediately shifts the conversation from nice to have to an absolute must-have for any serious production environment.
It absolutely does. And critically, it achieves that speed increase while also extending tool life because the constant flushing prevents that thermal shocking and rubbing caused by chips.
So you're saving time and you're saving on consumables.
You got it.
Okay, that undeniable productivity metric makes the case, but we have to address the elephant in the room, the cost of entry. Because we're not just buying a garden hose adapter here.
No, you are definitely buying a complex system. The upfront investment for a high-pressure pump unit and the integration is substantial. Like you said, the range is typically cited between $10,000 and $30,000.
That's a huge spread. Why the difference? What pushes a shop toward that $30,000 end of the scale?
It often comes down to the age and architecture of your machine. The lower end might be for a standardized bolt-on system for a newer machine that's already sort of prepped for it.
Okay.
But if you have an older machine that needs custom plumbing, a bigger pont, or complex integration with the machine's control, well, the engineering and installation costs push you toward that higher end pretty quickly.
And it's not just the pump, is it? This requires a full, compatible ecosystem. Tell us what else we need to buy or upgrade.
Think of it as plumbing from the ground up, all rated for extreme pressure. First, you need specialized cutting, tools, drills, end mills, you name it, with internal channels for the fluid.
Right. Through coolant tools.
Then your tool holders, they have to be sealed. A standard collet will just spray coolant everywhere. You need sealed collets or ideally hydraulic chucks that can handle that kind of pressure.
And the final piece, which I know we'll come back to later, is filtration.
Absolutely essential. Because you're putting this high-pressure system under immense strain, it needs advanced multi-stage filtration from day one. This is not just a standard strainer.
We're talking about filters that catch particles measured in microns.
Non-negotiable. And a big part of that upfront cost.
That makes sense. But let's play devil's advocate for a second on the ROI. What if I run a shop and say 80% of my work is high-speed milling of 6061 aluminum, where chips clear out pretty easily?
That's a great critical question.
Does that $30,000 investment still make sense?
For a shop like that, focused on soft materials and shallow features, the ROI will be much, much slower, maybe even negligible. Aluminum chips are light. They're easily cleared.
So TSC really shines when the challenge is the material itself.
The material toughness hardened steels, Inconel, titanium, or the geometry. Deep pockets, deep holes. If you can only use that 50% cycle time reduction on 20% of your parts, you have to run those jobs at a really high volume to justify the capital spend.
Understood. It's a performance upgrade for difficult machining. Now, what about operational trade-offs? That pump is drawing more power, so a higher electricity bill. You mentioned 10–15% more energy.
It does.
But you also said it can reduce coolant consumption by up to 35%. How do those two costs really balance out?
It's surprising, but the fluid savings are often very significant. A standard flood system wastes so much coolant through misting, evaporation, overspray.
Right, it goes everywhere.
The TSC system, because it's a focused jet delivered precisely to the cut zone, is highly efficient. That 35% reduction in fluid use can be a massive operational saving, especially with disposal costs and the price of good synthetic coolants.
So in a busy shop, the fluid savings could easily offset the higher energy bill.
In many cases, yes.
Fantastic. So we've covered speed. Let's shift our focus now to the quality of the finished part. For parts that need certification aerospace, medical surface finish is everything. What's happening at the cutting zone when chips aren't evacuated?
The enemy here is something called recutting or chip impingement. Imagine the tool slices through the material and creates a chip. If that chip isn't flushed away instantly,
The tool just drags it back across a freshly cut surface.
it's like dragging a piece of gravel over fresh paint.
A perfect analogy.
And because those chips are hardened, they act like a tiny piece of abrasive grit. They cause micro scratches, gouges, and they often lead to a defect in drilling called bell mouthing.
Bell mouthing. For anyone listening who isn't a machinist, what are we talking about here?
It's when the entrance of a drilled hole is slightly wider or flared out than the diameter deeper in the hole. It happens when chips start to pack up right at the surface, causing the tool to deflect as it tries to enter the workpiece.
And if you're making a part that needs a tight seal or a press fit, bell mouthing means that part is scrap.
It's a complete scrap. TSC resolves this by creating a clean cutting environment. Because the chips are blasted out the instant they form, the cutting edge is only working on virgin material.
Which leads to better results.
Demonstrably superior results. We see surface smoothness improvements of up to 10%. If you're trying to hit, say, a 63 ray requirement, a 10% improvement might push you safely into the 57 ray range.
And that's critical for sealing surfaces or reducing friction.
Absolutely. And beyond surface finish, there's thermal distortion. That trapped grinding debris must generate incredible heat.
Localized heat, right.
Excessive localized heat. And when material heats up, it expands, it distorts. If the machine is programmed for a specific dimension at ambient temperature, that expansion means the finished part will be wrong once it cools down.
I see.
TSC is just a hyper-efficient thermal removal system. It keeps the cutting zone significantly cooler, which reduces that distortion and ensures the final part holds the tightest possible tolerances.
So TSC moves you out of this reactive cycle of compensating for problems and into a purely accurate predictive cutting process.
Mm-hmm.
The benefits are clear: massive speed, superior quality. But now we hit the final and maybe the most crucial reality: maintenance.
This is the high-stakes trade-off. Let's look at the standard system again. Its maintenance is simple. Clean the tank, empty the strainer basket.
Maybe swap out a simple pump every few years.
Exactly. Failures are annoying, but low cost.
Yeah.
A clogged nozzle is $50 and 15 minutes of downtime.
Now, bring us back to the 1,000 PSI high-pressure world. Where is the catastrophic vulnerability?
The Achilles heel of any TSC system is the spindle's rotary union. You have to picture this component. It's the gateway that transfers pressurized coolant from the static plumbing into the high-speed rotating spindle.
And it does this using incredibly delicate internal seals.
Seals operating under constant, extreme pressure. They're engineered to handle the pressure, but they cannot handle grit.
Which is why that advanced filtration is so critical.
It is everything. If your filter fails, or if maintenance is neglected and abrasive fines, tiny particles of carbide or metal are forced into that rotary union seal under 1,000 psi.
It's effectively sandblasting the seal from the inside.
It destroys it. And once that seal fails, pressurized coolant floods the interior of the spindle and contaminates the bearings. This is not a simple fix.
We're talking about a catastrophic failure.
Catastrophic. Often a full spindle replacement or a rebuild that costs tens of thousands of dollars and means weeks of machine downtime.
That is a staggering operational risk to mitigate. So the maintenance schedule needs to reflect that you're protecting the most expensive part of your machine.
Yeah. It has to be rigorous and it has to be proactive. Standard maintenance just doesn't cut it. TSC systems demand daily pressure monitoring.
If the pressure drops, something's wrong.
They require weekly inspection and cleaning of those filters, and monthly checks of the rotary union for any leaks or wear. It requires constant, highly trained operational vigilance.
Which brings us to the final synthesis of this deep dive. You have a system that offers verifiable, guaranteed 50% productivity gains and superior quality. But it requires constant, skilled human interaction to prevent a catastrophic, multi-thousand-dollar failure.
That's it exactly. The choice isn't just about money, it's about operational culture. Standard coolant is forgiving and low cost, but it's limiting. TSC unlocks aggressive performance, but it demands an entirely new level of commitment to discipline.
So we leave you with this final provocative thought. If a shop commits to the financial investment of a TSC system, how should they weigh that hard calculable ROI against the constant demand for perfect, human-driven vigilance?
Is the risk of that costly failure worth the reward of guaranteed speed? Or should every shop incorporate the cost of highly trained daily monitoring into their ROI calculation from day one?
The technology is ready, but the human element is the ultimate failure point.
That's the real trade-off you face when transforming your machine shop.
Food for thought. Thanks for joining us on The Deep Dive.
Thank you.